It's a pleasure to introduce Macarena Arenas of this parish, who will speak to us about Taut smoothings and short geodesics.
Well, thank you for having me here, and thanks all for being here. The objects in this talk are going to be surfaces. The surfaces can be closed or can have boundary components, but they're always going to be compact for us today. Surfaces can be of two types. They can either be purely topological objects. Okay, maybe before that I should say something else. They're always going to be non-positive record or negative record. They are going to be orientable. This is an important assumption. And they are either going to be topological objects, or they are going to come endowed with a Riemannian metric. On the surfaces, we're going to be looking at curves. Is this a good color? Can everyone see the color from that? So curves are going to be either closed curves or arcs, and they can have self-intersections, that's fine. And when I say curves, so closed or arcs. If I mean arcs that are properly immersed. So the endpoints are on the boundary, and they can either move on the boundary or they are fixed on the boundary, but I cannot homotope them away from the boundary. Okay? And again, curves are going to be one of two kinds of objects. Either they're going to be purely topological, in which case I'm going to ask that they intersect transversally and are in general position. What does this mean? This means that I don't want intersections that look like this, right? Those are not real intersections. And I don't want triple intersections or multiple intersections. All intersections are just double points, okay? And if they're not topological, they're going to be geometric objects. And they're just going to be geodesics in the corresponding Riemannian metric that we're putting on the surface. Okay, so these are the objects. This is what we're going to be talking about today. What do we want to know about these things? So the goal is to understand what is the interaction between the geometric information and the topological or combinatorial information. Okay, so that is of course a very big goal. So maybe let's give some examples of what kind of situations fall within this goal. What are the basics? So let's see. Let's start with that. Every free homotopy class of either arcs or closed curves contains a geodesic representative. So this is purely topological stuff, but we're saying that in this homotopy class, there is something geometric, a geodesic representative. Another thing we know is that shortest geodesics self-intersect minimally. within their homotopy class. Okay? So what does this mean? If you come from the intuition of hyperbolic geometry, this might be a confusing statement, because in a hyperbolic metric, there is always a unique geodesic. But we're thinking about arbitrary Riemannian metrics, so there might be many geodesics in each homotopy class, and the only ones that we know that intersect minimally are the shortest ones, the shortest within the homotopy class. Okay? That makes sense to everyone? Okay. And the last thing that I want to say here, I guess, is every minimal configuration and I will say what that means in a second, corresponds to a geodesic in some metric. And this is by work of Haas and Scott. And Neumann-Kott, which, by the way, I wrote it, but I didn't say it. The results in this talk are joint work with Max Neumann. Okay, so what do I mean by a minimal configuration? If I have a curve that self-intersects minimally, so here's a curve that self-intersects minimally. It's not unique up to isotopy, generally. So this is going to be homotopic to another curve. Let's see if I can draw it. These two are minimal configurations, okay? Different minimal configurations. Each one of these is a geodesic in some metric on the surface. Here, it's important to highlight that this is an arbitrary Riemannian metric. If I want to say hyperbolic here, this is no longer true. One of these two curves cannot be a geodesic in a hyperbolic metric. And that is very easy to prove and very nice. So if you want to know about it, I can tell you in the end. But yeah, so this is for arbitrary Riemannian metrics, okay? Right. So these are the basic objects. How do we study these objects? So we're going to be looking at a thing called the length spectrum. So this is a set that depends on the surface and on the metric that you put on the surface. It's a set of lengths of all shortest essential geodesics, okay? And there are two variations of this set. So if we're looking at arcs, we can either consider geodesics relative to the boundary of the surface, or geodesics relative the pair of endpoints that we're fixing on the boundary. Okay? So that's just something to keep in mind. Okay, so these are sets. What can we ask about these sets, or what do we know about these sets? So the first thing we know is that the length spectrum is discrete. That's a nice fact. And if we make it into a function, if we make this into a function that each homotopy class assigns the corresponding number, that is called the marked length spectrum. And at least when the surface is negatively curved, that determines the metric uniquely. So I think that's a very nice fact. Okay, so this is a set. It's a naturally an ordered subset of the positive reals. So we have some points in the length spectrum. What can we know about this? What can we want to know about such a set? What is a natural question? Maybe what is the first point? No? So the first point is called the systole. Yeah. So the systole, or asystole, is a shortest essential geodesic in the surface. Okay, and here's a fact about systoles. They are simple. Simple means that they have no self-intersections. Okay? And this is true almost always. And you will see from the proof what this means. Okay, so let's prove this claim. Assume that this is not the case. Assume that you have a systole that has self-intersections. So alpha is a systole with self-intersections. Let's draw the simplest example. Maybe it looks like this. Here's my curve. Here's my surface. So what I can do is I can do a little surgery around the intersection point so that I get something that has no intersections. Okay? So I want to prove that these things are always simple. I have to somehow get a simple curve from this object. Okay? So if I have self-intersections, I can try to do one of these two operations. So this is one, this is the other one. And they give me the following two results. So one looks like this. The other one looks like this. And each of these curves individually is simple or has less intersections than the original curve. And after you tighten them to be geodesics, because after doing the surgery they're not geodesics anymore, they are shorter. All of these curves are shorter than the original curve. So why are we not done yet? What's missing?
Some of them might not be essential.
They might not be essential. So at least one of these three curves is essential, so long as you're not in a pair of pants. So that's the sort of almost always here. If you're in a pair of pants, the systole has exactly one intersection, but in every other case, the systole is simple. Okay? So that's the proof of this claim. And that gives us 1 point in the length spectrum. Yes?
Is it clear when you put type you don't introduce new such intersections?
It's true. It's not like trivial.
No.
Yeah. Right. Okay. So this gives us a point in the length spectrum. There are many other points. Maybe we want to study other special points. So what are other special points that we could study? So we can define a K-systole to be a shortest geodesic with at least K intersections. And what we have just proven is that zero systoles have exactly zero intersections. So now the question, the natural question here, which has been asked by a number of people, because Mahian, Busser, Chaz, and others, is the following. So do K-systoles have exactly K intersections? So I think this is a natural question, because if I ask you for the shortest curve with at least 2 intersections, and you tell me that it has 100, that sounds counterintuitive. That sounds like it shouldn't be the case, right? So what do we know about this question? So we know that the answer is yes. For K equals 0, we just proved it, at least in the case that you're not a pair of pants. We know it for K equals 1. That's a theorem of Busser. And we know it for infinitely many values of K, but depending on the metric. That is to say, I fix a metric on the surface, then there are going to be infinitely many values, depending on that metric, for which the answer to this question is yes. And that sounds like it might be like a very deep fact, but actually it's very silly. Assume that you have a k-systole with k plus n intersections, then that is also a k plus n systole. And for that value, it satisfies the question. Yeah, so yeah, I don't know how much information you get out of that, but you know it? Okay, so this is all we know in the compact case. When the surface is compact, we have no other results that tell you anything about this question. When the surface is not compact, the geometry is a bit different, and we know a bit more. So there are results of Parlier and Erlandson in this direction, and there are results of handball. So handball, for instance, proved that if your metric is hyperbolic, then for a large n of k, depending on the metric, for every bigger value of k, the answer to the question is yes. So we know a little bit more when the surface has punctures, but we know almost nothing when the surface is compact. Okay? So here's a corollary. Corollary of what? The answer is yes for arcs with fixed endpoints. And the answer is almost yes for arcs with free endpoints. Almost yes, what does that mean? Just to quote a pair of famous mathematicians, this program is sometimes derailed by uncooperative facts. There exist arcs with free endpoints that do not satisfy this. So, like, the shortest geodesic with at least k intersections is going to have k plus 1 intersections. Like, one can give explicit examples, but that is the worst thing that can happen. Okay? So that's what I mean here by almost yes. All right?
Actually, your endpoints always lies in the boundary also.
Yes. So yeah, curves are properly immersed. You're never homotoping the endpoints away from the boundary. Okay. Any questions so far? All right. So let's get to the topology. So a smoothing is a surgery that you can perform on a curve. So you have a curve with self-intersections. The curve comes with an induced orientation that you can read about around the intersection point. Okay? And the smoothing is one of the following two things. So you're deleting a neighborhood of the intersection point and you're rejoining the arcs. And how are these two operations different? One of them preserves orientations, so the result gives you something that is already oriented, and the other one does not. Like if I try to orient this, I don't get anything sensible. Okay? So this is called an unoriented smoothing. This is called an oriented smoothing. And it's a fact, an easy exercise if you like, that this operation always gives you something connected. The result of performing the operation that doesn't respect orientations is a connected thing. It's a curve again. Okay? So this is connected. And for the rest of this talk, when I say a smoothing, I mean this operation. Okay? So we're going to say that a smoothing is Taut if the result of performing the operation is a curve that is in minimal position.
Isn't it the other way around? Can you see example of two curves intersecting?
1 second. So
in the example beyond.
So here, the operation that disconnects is the one where I'm preserving the orientation, right?
Okay, I see.
Right, okay. So a smoothing is taught if the result is in minimal position. Okay? The curve cannot be homotoped to have any fewer intersections. So let me give you an example of what we have in mind here. So here's a curve on the surface. If I perform this smoothing here, then I can homotope the curve to remove all the intersections. Do you see that? Is that clear? If instead of doing that, I perform this smoothing, then I cannot do anything else. That's already in minimal position. Okay? So this is the kind of thing that we're after. So what is the question now? The question is, does every Taut curve have a Taut smoothing? Oh, sorry, I think I never defined a Taut curve. A Taut curve is a curve with minimal self-intersections. Okay, so that's question. Does every Taut curve, so a minimally self-intersecting curve, have a Taut smoothing? Okay, so I think this question is interesting on its own right. I think it's a very natural operation, and I think it's something very natural to ask about it. But maybe you don't, so let me try to convince you that it's something interesting. Let's see. So let's assume that the answer to the question is yes. If that is the case, now let me take a k-system. That intersects more than k times. So alpha has, say, k plus n intersections. Now I know, because I'm assuming that the answer to this question is yes, that I have a Taut smoothing. So let me take that Taut smoothing. Alpha prime is Taut smoothing. That means that this curve has exactly one intersection less. So intersection number of this curve is k plus n minus 1, which is greater or equal than k. So it still has a chance of being a k-system because it has at least k intersections. And now, because of the same reason that we explained here, when I remove the intersection, I am making the geodesic in that homotopy class shorter. So now, the geodesic, let me write it this way, the length of the geodesic representative in this homotopy class is less than the length of the original geodesic. Okay, which is a contradiction. Okay. So we have shown that if the answer to the question B is yes, then the answer to question A is yes. So I don't know. That's a reason why you might care about question B. All right. So what makes question B hard? So sort of what's happening here is that if you just try to perform this operation at random, you're likely going to get something that is not Taut. So there are examples of things that have, say, there are curves that have any number of intersections. And only one Taut smoothing. So if I choose the wrong place, I'm screwed. And there are examples of curves, again, that have any number of intersections, and where some smoothings remove all the intersections of the curve. Okay, so you don't have to believe me. I have examples. So this curve only has one Taut smoothing. It is this one. So if I smooth this intersection like so, that is going to be Taut. None of the other intersections work. You don't have to believe me, you can check that yourself. And in this curve, if I do this smoothing, I'm removing all the intersections. I think that's a bit easier to see. And these constructions are kind of generic. I could have gone around more and more times before closing the curve, and the same phenomenon would be happening. Okay? So those are examples of these two phenomena. Okay? So, okay, the question is now, how do we tell if a curve is Taut? So let me state that.
Is the smoothing being taught the only way to know that the length went down?
No. So a positive answer to question B implies a positive answer to question A, but it's not clear that it has to be an even only if. Right, okay, so here's the fact.
It always goes down, but only just by one. Right?
That's the point, yes. Because if you do a smoothing and it removes all the intersections, then you get no contradiction in that argument. Right, so here's a fact. A curve is Taut if and only if it has no monogons, bigons, and in the case where a curve means a curve, an arc with 3 endpoints, we have to add a third possibility, which is a half bigon. So what do these things mean? So monogon is a disk with a single corner. So this has no topology inside it. Bigon is a disk with 2 corners, and a half bigon is a triangle that forms with the boundary of the surface, like this. So here again I have a disk, and I think in all of these cases you can see that there's a homotopy that reduces intersection number. So why is this? I mean, these pictures look very easy. Why can't I just draw the curve and check for these objects? The problem is that these things are not embedded, and in principle they don't even have to be immersed. Okay? These things, you see them this way in the universal cover of the surface. Okay? This ring is defined in the universal cover as the intersection between 2 different lifts of the curve in the universal cover. Okay? If you want to see this object in the surface, it can look very tangled, and then it's very hard to find it. Okay? I mean, for instance, in these examples, can you see the bigons or the monogons? It's not like so easy. Okay? So what are the good news? What tools do we have to try to understand these objects? So there are some results of Haas and Scott that help us here. Right, so if you have a curve that is not Taut, on an orientable surface. Then that curve has to have a small monogon or bigon. Okay, so what does that mean? Small means that the projection, so we're thinking of these objects as living in the universal cover of the surface, and then they project to the curve in the quotient in the surface. So the projection can only fail to be injective in finitely many points. And in the case of a bigon, the other thing that you want is that the corners of the bigon, so the vertices, don't project to the same point downstairs, okay?
This finite number depends only on the surface and on K.
I don't think so. I'm not sure there's any sort of results about that. Okay, I mean, I don't know if this is clear just from what is written. So let me give you some examples of how you can fail to be small. So this is not a curve, this is a multicurve. And that's exactly the point. This theorem doesn't hold for a multicurve. So I have some topology here. And here I have a bigon. Let's see if we can follow it. It starts at this corner. Right? And if I start following it, I go around. And when I get here, this arc, I'm using it again. So the projection is very much not injected. Is that clear? Okay. And this picture can happen if you have a curve in a non-orientable surface. So if instead of this, I have on this, so this lives kind of in a Mobius strip if you want or whatever. Well, not in a Mobius strip, in a higher genus non-orientable surface. Then this again has this bigon that intersects itself in a whole interval, and that's the only bigon. There's no other one. The point of this theorem is that if this happens in a curve on an orientable surface, then that's fine because you can still find a bigon where the worst thing that can happen is that you have like, this is not a very good picture. The worst thing that can happen, something like this. I don't know. So I'm intersecting myself just in isolated points. All right? And maybe that doesn't look much better, but it makes our life easier. So I mean, these theorems, I don't know if it was clear, but this corollary is a corollary in orientable surfaces, and the theorem that it is a corollary of is something that works, again, only in orientable surfaces.
So the bigon, sorry, just to be, I think something I got was the bigon is just the pair of curves that's
Yes.
right, it's not the interior.
It's not the interior. It's not the interior. It's the pair of curves. Okay?
Up to now, you used hyperbolicity somewhere.
I'm not assuming hyperbolic metric. I'm assuming. Oh, okay. So this is all combinatorial. This part of the discussion is all combinatorial. And the metric part is about Riemannian metrics. So I'm also not assuming hyperbolicity. Okay. So this is sort of the tool that lets you prove things about these objects. Otherwise, you would be lost. You would have no tools to work with. And what is the theorem that we prove? Should I erase this? That's fine. So the theorem has three parts. A, if we have an arc with fixed endpoints. then the arc has a Taut smoothing. If we have an arc with 3 endpoints, then we don't necessarily have a Taut smoothing, but we have a smoothing that can only be homotope to have one intersection less. We have a smoothing. Let me write it like this, that removes at most one extra intersection. And this is optimal, so let me make a note of that. So here's an example. Let's see, can I draw this by hand? Oh, why not? So here's a curve. This is the boundary of the surface. Here's some genus. This thing that is not an intersection is just saying that I'm going over some handle in the surface. Okay? Maybe I didn't say that before, but also here, when there's no intersections drawn, I'm just kind of imagining that the arc is going through through some genus. Okay? So this curve has only 2 intersections, so it has only 2 smoothings, and they look like this. So here's one, and the other one is symmetric. Those are the 2 smoothings. And neither of them is Taut. In both of them I have a bigone here, a half bigone here. And there was no half bigone in the original curve, so the original curve was Taut. Okay? So there's nothing to do about this. This is the best that we can do. That's just reality. Okay, and there is a third part of the theorem. I keep losing erasers. So, third part. For curves, so let me state the theorem in like a very vague way, and if you really want to know the details, I can tell you later. So if you have a Taut curve that satisfies an extra condition, then the curve has a Taut smoothing. What I can tell you right now about this extra condition is that it seems fairly generic. Not necessarily in like a probabilistic or precise sense, but if you draw a curve at random by yourself, it's likely going to satisfy this condition. We don't really know exactly how generic it is in like a precise sense, but it is a condition that is easy to satisfy for curves. Okay? And just maybe let me make another note. These results are algorithmic. I'm not just telling you that there exists a Taut smoothing. I can find it for you. I can tell you how to find it. Okay? Any questions?
How to find it?
That's kind of the proof of the theorem, I guess. So I suppose that the next thing we should do is sort of discuss what goes into the proof of this. Right, okay. So these examples that I drew here, they weren't just to say, oh, look at how hard this problem is. The point of these examples is for you to kind of recognize that this is a global problem. We are doing an operation in like a very local part of the curve, but it's affecting globally what's happening. Okay, so we're not going to be able to detect whether there's a Taut smoothing by just sort of looking locally around the intersection point. We need something, we need some kind of measure or some kind of way to recognize which intersection points are better, like globally in the whole surface. Okay, so how do we do that? So the ideal thing would be to be able to maximize or minimize something that you can measure on all the intersection points of the curve. And here we do take inspiration from hyperbolic geometry. So if the surface had a hyperbolic metric, then I could measure angles. Okay? And angles turn out to not be exactly the right thing to use here, because angles, the hyperbolic metric is not invariant under performing triangle moves. So I can change the curve within its homotopy class, and the new isotopy class that I get is not going to be a geodesic in the same manner. So that's a problem for us, but we can try to define a combinatorial version of angles. That's what we're going to do. So we want a measure that is invariant under triangle moves. If I look at an intersection point and I perform a triangle move, I want the angle that I'm measuring to be the same around that intersection point. Okay? So this is defined in the universal cover. I'm going to be looking at the lifts of my curve alpha to the universal cover. And these intersect in some way. So let's say I want to measure, the combinatorial angle here. So in this intersection point, what I'm going to do is I'm going to look at all the other lifts of the curve that intersect this way. So they intersect both of the arcs that form the section, and all of the ones that go this way. And this is a finite number. Of course, there's infinitely many lifts in the universal cover, but most of them do something like this. Okay? There's finitely many that intersect in this direction, and there's finitely many that intersect in this direction. So the combinatorial angle at this point is going to be the number of lines that intersect, let's say, horizontally. Divided by the total number of lines that intersect both horizontally and vertically. Okay, that's going to be our definition of angles here. This turns out to be invariant under triangle moves, and it has another property that we want. So what is the other property? So if we have a curve that has a triangle, and we perform a smoothing in one of the corners of the triangle, we're immediately creating a bigon. So we already know that triangles are bad for finding Taut smoothings. As soon as I do a smoothing in the corner of a triangle, I'm in trouble. The problem is, again, that this triangle could be hidden, it doesn't have to be embedded or anything in the surface. But one property of hyperbolic angles, and also of these combinatorial angles, is that if you look at a triangle, sorry, I'm not sure if you were able to see what I was trying to do. Have a triangle. I have an angle here. What happens with the opposite exterior angles of the triangle in hyperbolic geometry? What would you expect? If this is a hyperbolic triangle, I have this angle here. What happens with the opposite external angles? Come on, people know hyperbolic geometry, no? They are bigger, right? So these angles here And this turns out to also be true for the combinatorial measure that we're defining here. So if you take the maximum of all combinatorial angles, that guarantees immediately that is not that the vertex at which you are looking is not the corner of a triangle. Okay, so that is what gets you started. It's not enough to check that you don't have triangles. Am I doing on time? Yes. What else can go wrong? So there is a lemma that we proved. That says that if you have a Taut curve, and alpha prime is a smoothing. So it's not a Taut smoothing, just any smoothing. If this smoothing is not Taut, then we want to know where the small digons and monogons can come from. And so then a small digon has to come out of one of these four pictures. Okay, so one is the triangle that we already saw. Again, I'm drawing these pictures in the universal cover. This is just a triangle that projects to a triangle downstairs. The other thing that you can have is a triangle that in the projection, these two vertices are identified. So let's see if I can draw it. Yeah, okay, so I'm not sure if this is a very nice picture, but you can see here there's a triangle, and I identified two vertices in the quotient. The other thing that can happen is that you have a quadrilateral that looks either like this or like this. We call these trapeziums and we call this rhombi. So what is happening here is that these two vertices are identified in the quotient, and what is happening here is that these two vertices are identified in the quotient. So this is happening in the original curve, in the universal cover of the original curve. And if I'm performing the smoothing at this intersection point, then I'm smoothing these 2 points at once, and I'm creating a digon. And we proved that these are the only 4 pictures that can arise from a Taut curve. So we already maximized something that tells us that we're not performing a smoothing in a triangle. And now the tricky part is getting rid of also these 2 pictures. And that's why the theorem has some extra conditions. But this is kind of the idea of the proof. Any questions? No? All right, maybe let me just sort of close with 2 questions. So one thing that I would like to know is if a random curve has a Taut smoothing. So maybe one can apply this theorem to try to prove that a random curve satisfies this condition. I don't know. Again, random here is not well defined, but it can be defined. Like one can define models that make this precise. And the other thing, again, we're using very heavily this theorem of Hassan-Scott, which only works if you have an orientable surface. So what happens if the surface is non-orientable? And I mean, of course, the big open question is still whether closed curves, Taut closed curves have Taut smoothings in general. But I mean, that's obvious. That's still a question, right? Does a Taut curve in a non-orientable surface have a Taut smoothing? Okay. Thank you for your attention.
Questions for Macarena?
What is a random curve?
I mean, so there's a model defined by Algab and Gaster, for instance. There are ways of making it precise, but I don't really know off the top of my head the definitions.
I could just go around and walk on the surface with it.
Yes?
So for the hyperbolic surfaces, it's known, theoretically?
No, even if you're just assuming that the metric is hyperbolic, we don't know that curves have Taut smoothings. Sorry, that K-systos have K-intersections. Yes?
Did you say where it were? I mean, exactly it matters that it's arcs rather than with curves?
I did not. Basically, we prove a theorem that is that encompasses these three cases, and where you have this extra condition. And what you do is you show that if you have an arc, you're always satisfying this extra condition, basically.
And is the extra condition something to do with these angles, or something?
Sorry?
Is the extra condition framed in terms of these angles, or is
It's more like framed in terms. I mean, I can say it. It's not like so complicated. So the extra condition is that you have an unoriented angle. So when you're looking at, sorry, an unoriented corner. So if I'm looking at this corner, for instance, I want this to not be consistently oriented. I need an unoriented corner that is not the corner of a quadrilateral or a pentagon. On one side. On the other side, anything can happen. But on this side, I want to not see a quadrilateral or a pentagon. And there's another condition that we have, but it's more artificial. This is the main one.
Any further questions? If not, let's thank Macarena again.